Well, hi and welcome to my shop. Almost just looking out at my two cats there. It's a beautiful, beautiful sunny day. Good day for working on a tube tester, or tube testing. It's not a tube tester. So a little bit of explanation here, but things haven't changed a lot since the end of the last video. What I've done is I've changed the power supply for the heater of the tube here. Before, the tube was receiving power, heater power, just from my oh so cool power supply here. But this thing is quite limited. It just produces 6.3 volts, at least it declares 6.3 here. So what I've done is I've switched from using this as a source to using this power supply back here. This is a very strong DC power supply. That thing will put out 10 or 20 amps at 6 volts. It's quite powerful. At 20 volts it'll put out 10 or 20 amps, so it's quite strong. The problem with it is the lowest output is 6 volts plus or minus. It could be 6 volts, but it could be 6.5 volts. If it's 6.5 volts, there's a chance I really can't use it to power this tube. So the first thing we got to do is find that out. Now it does have a couple meters up here, an amp meter and a voltmeter, but they're both kind of get the word right, imprecise. So we can't rely on those for the precision we need down here. So the way this works, if I remember what I was doing, the current flow to the heater goes through this meter as an ammeter. There's some comments about this meter disturbing the current through it, or the voltage or something. I don't see how that can happen. It's just an ammeter. Yeah, it has a tiny voltage drop. So to compensate for any loss of voltage that might occur there, I have a voltmeter monitoring the heater temperature right here, right at the pins. And that voltmeter is which one? Which one is it now? That one is this one. So this is going to show us the heater volts. Whoops, this one. Which one? The one that's out of sight. This one here. So that's going to show us heater volts. Let's just get this through my head. Current, volts. Good. This is showing grid voltage. This is showing plate current. This is showing plate voltage. This is showing whatever I touch the probe to, which I still have at least one flexible meter here. I still have this resistor in. You can just barely see it in the picture. Set to something cockeyed right now, 1,000 times. It's set to like 100,000 or something. I don't know what I'm doing here with this anymore. I may remove this. I think I'm going to remove this right now, in fact. Let's take this out. Didn't seem to help the situation any. So this was in the plate circuit. I'm certain tests that you need a resistor in there to allow. Okay. Never mind. No need to finish sentences here. So we'll turn everything on. No. Let's not do that. Let's start with just what voltage comes out of that power supply. It's set minimum right now. And I'm a little worried with the tube sitting right in here. I'm going to whack it with, well, my experience is this thing doesn't put out much over 6 when it's at its minimum. So let's go with it. So we'll risk the heater here a little bit. And the heater voltmeter, heater voltmeter is this one here. I'm going to get confused, I know it for sure. Okay, so I have all these different meters with all the different settings and different quirks. I believe I have this one set on voltage now. DC volts, looks like it. Heater voltage. So we want this to say nominally 6.3. And we also want this current flow to be 0.7 of an amp. 0.7. 700. Okay, so I'm just, wait a minute, no, this is the plate current. Come on, man, this is the, come on, Jim, come on. Remember, I just got to remember everything here. Oh, it's no longer AC current, it's DC current. DC auto ranging. Okay, I think we're set now. So the objective is pay close attention to this right off the bat and see if this guy is jumping way up over 6. You know, there's a thermal, there's a time delay in heating these things up, so 7-8 volts, I'm not going to burn this thing out. In fact, 7-8 volts continuously won't burn it out. So let's stop worrying and hit the switch. Here we go. The big pile of nothing. So on this meter up here, it says 5.5 volts. What happened to it? Why didn't it make it out here? Here we go. The 2 leads are here. Here. Oh, this is hooked up solid. I mean, this has to work. This has to work. Okay, so I probably got a problem here. I'm on the 10 amp scale, but in the milliamp range. So we're gonna move this. Do it live. We'll do it live. Oh, that's right. Yeah, here we go. There we are. Yikes. Yikes. Keep coming down. Down. Oh, so I've just heated it up. That's what that is. Well, that's interesting. So you saw the initial heater current was well over an amp. Excellent. And the voltage we're showing here is 4.8. Way low. Way low. But this is pretty close. How can this be so low and this be so close? The questions just never stop. Well, one answer could be because I'm not doing what I think I'm doing. That could be one answer to this. I'm pretty sure this is correct. Why don't we double check it? I have a meter to double check. Double checking always results in interesting stuff. Now the heater is in a totally different circuit from the rest of this. So I'm going to use this meter. I'm going to need to ground its lead to the correct place. It's the master ground. It's the master ground here. Or I got to get another meter. I don't have another meter. I'm out of meters. I got every meter on here now. Do I have another meter? Got one hidden away somewhere? Oh, okay. So I got to. You know what? This is not on the pin. What's this doing hanging off the tube? It's supposed to be on pin number 8. Cathode pin. Okay. Well, we're just fooling with the heater right now, so it doesn't matter, but it could be. I'm trying to think of why this thing didn't work the way I expected it last time. And probably the best answer to that question is because my expectations were bad. Okay, so we're going to try to ground all these onto this. This is the cathode terminal here. Yeah, let go of those. Hold on to a bunch of clip leads while you're. I don't know. This isn't going to work. This is not going to work like this. Oh, everything's coming off everywhere. We're going downhill here. Let me put this one back on. This is 2187. 7. The tube is warming up. That's fine, because we're under 7 here. If this meter were like 800 or 850, I'd be a little more worried. And you might hear a new sound in here you don't normally hear. That's the cooling fan on that big DC power supply. In case you can hear that. Okay, let's solve our problems here. Okay, I'll put this onto the correct one now. 8. And hook up all these grounds. Now, just because I make mistakes once in a while, just once in a while, let me just take a closer look at the Where's my magnifier? The numbers on here. I just want to be sure I got the pins right. 3. Okay, let's just try eyeballs. Not with this. Okay. No doubt about it. Something fell here. What fell? I don't know. Okay. Cover that up. Now we'll hook up all our little grounds here. Now, there's no high voltage or anything being supplied to this at this point, so it's all quite safe. So that frees up the ground to my voltmeter so I can make a measurement. That's probably what I heard fall. It's probably the ground leak. Where'd it go? Here it is. Okay, now with this, and ready. Okay, now I want to hook this up to one side of the heater. Just making sure nothing funny happens there. There was an occasion in my life where you saw me tapping that just to see, you know, in case. I'm sure any of you who do this kind of work do the same thing all the time. When you go to hook something up, you gotta tap it. I have a little story I'm going to tell you when I was working at the power company, and I had a very odd job. I was a corrosion technician, and it involved measuring DC current flowing in, accidentally flowing, called straight current, accidentally flowing in the wrong structures, like water mains, the power system neutral line, gas pipes. And where's this DC coming from? From streetcars. So I had an occasion, I won't go into it, but it's an interesting story in itself, but I had an occasion to ground a lead, a great big clip lead, like one of these, only times 10. Just hold it on the streetcar tracks while I made a measurement. Okay, I'd made an error in what I was doing. If I thought about it a little harder, I wouldn't have done that. Streetcar tracks are in the road, in the public. So I wait for the traffic to kind of stop. All I got to do is run out, go like that on the track, and my partner's going to make a reading on the meter. Just take a moment, and I'll run back off the road and the cars can go by. Do this kind of stuff all the time back then. Well, not this one test, anyway. So I grab the lead, I go out on the road, I put it down, there's a bang so loud, I think my hand is gone. I look down, half of the clip lead, the grip part, one whole half is gone. It's just gone. I'm freaking out, I'm out in the middle of the road. So, those kinds of experiences put the fear of death in you. And the result is, in your shop, you tap little clip leads. Okay, enough of a story there. I didn't get hurt, just my ego and one clip lead shot. I should tell you more about that story, but I won't do it now because it's quite interesting why I was doing that. Now, getting back to this situation. So we're still reading so we're checking the 4.9. That's what we're doing. Yeah, now I remember. Okay. Get these two leads in my hand. I'm all set. Just catching up with myself. Okay, so we're on DC 15 volts. This might go backwards. Going backwards. Okay, here we go. So what is the voltage there? Make sure that's set right. So this voltmeter says 4.8. Wow. 4.8, but we've almost got the right current. 4.8. So let's crank it up. This is now believable. I verified it. In fact, I mean, this is a digital meter. What are the chances that there's something wrong with this? Pretty low. Let's take it up. We'll watch the current and the voltage here on the heater. We'll see. Maybe the current won't go up as much as I expect. So the current's going up. Let's set the current to 0.7. where it's supposed to be. That's about as close as I'm going to get. So it's only 6 volts. What happens if you put 6.3 volts here? Let's find out. There's, whoops. Oh, it's like a hair trigger on this setting. There we are, 6.3. So a little over 7. So, you know, they might have made allowances for voltage drops, knowing that, you know, the supply transformer will put out 6.3, but 6.3 won't make it to the heaters. So, you know, maybe the 6.3 is really 6.5. Who knows what they're doing with these radios. But I think what I've learned is there's a sensitivity issue here around the heater voltage, heater current that I've ignored all my life. I've ignored that. But now I can't ignore it anymore. I have seen the truth. And the truth is this is really, really accurate. 6.3 volts and 0.70. That's really accurate. It's really, really accurate. That's the truth. Okay, so about a good 70% of what I was just muttering about really isn't worth hearing, but it's too bad it's out there now. So where do we go next? So now we have a stable, properly heated heater in here. Should turn everything else back on. We could try to repeat the static measurement, but no, I'm going to try, because I'm already hooked up to the scope. I think I'm hooked up to the scope. Let's see if we can't repeat that. Just level out another camera here. Okay, so I'm going to switch on and set up all the equipment. This guy first. Okay, so that sets up the oscillation that's going on to the grid. Scope to see the results. These wires are kind of in the way. Okay, there's our 2 traces. One output, one input. I can't remember which is which offhand. We should be able to find out if I just turn this up a bit. Okay, so here's the input. Can't be the output. There's no power on the tube yet. Let me just move this light. I'll move it up. Okay, next we start up the DC voltage. So let's put the grid monitoring meter on. We have the plate monitoring meter and we have the plate voltage monitoring meter. Okay, put our frequency counter on. So we're just about ready now to actually apply some DC. So we'll do this in order also. So the B plus is zeroed. Okay, we'll turn that on, let it warm up. Now there's no more 6.3 volts coming out of here feeding the heater. That's gone. So we just have the C minus voltage and the B plus voltage. And there's an interesting comment on one of my earlier videos about where those letters come from for A battery, B battery, C battery, and then the part I found so interesting, and what I'm sorry I can't think of your name, but it's there anyway, was where did the AA and AAA come from? And of course it's just one of these numbering systems that starts out A, B, C, D. Now you want to put something between B and C, but there's no letter. So now which one? Who's beeping? Who's beeping? Okay, it's either this guy or this guy. I don't know. I'll leave him beeping. There's 2 meters beeping here. I think what they're saying is, hurry up, man. Get focused. Okay, so we're going to raise the... didn't raise it up very much. This should be the C minus voltage. I'm expecting more like 14 here. How come it's so low? See, am I doing the right thing here. Take that off. Heater voltage. Grid voltage. Let me just quit. Yeah, this guy. Oh, this guy too. These meters are useless in a situation like this. Now, what if everything we had in the house beeped at us every 5 minutes to tell us, hey, I'm still on? Wouldn't that be great? Okay. That's just totally out. So I was looking at this and trying to decide if somehow the supply voltage is supplied. Oh, there's something with a ground off. Oh, this is the signal in. Not grounded. Okay. Grounded that. And my scope display. It didn't appreciate that, did it? Hey. Okay, not quite sure why my scope display disappeared. It's no longer triggering, maybe. What happened? Let's put it online. I'll force it to trigger by just putting it online. I have some trigger problems with this scope, so we'll just make it trigger on the line. This should be the input. Yep. And here's the output. Here's the output clip. Let me just, how did I get up? Well, that was up so high so you could see the power supply. Okay, enough of that. So this guy should be on the output. This guy needs to be connected down here. Now yeah, so I took that resistor out and I've hooked a scope across the plate and cathode. If the power supply is really good, the DC power supply, then it really doesn't matter what I put on the grid. You'll never see anything on the plate. It's, I don't want to say it's kind of being absorbed by the power supply. It's not really the right way to put it, but so I need this resistor in the plate circuit so I can catch something to put on the scope. We have plate current flowing now, do we? Shouldn't we see a plate current here? No, I have no plate voltage. Let's raise, just for now, let's raise the plate voltage, make sure current flows, just to make sure everything's set up here. And there it is. There's the current flowing. And what do we got? And so this meter's coming up too. Just a low voltage there. And just as I predicted, absolutely nothing on the output. So, I want to bring back the resistor here. We'll reintroduce it into the turn off the B+ supply. So we'll introduce the resistor into the plate circuit and then try to read across it. That's kind of the idea. Maybe I had the scope leads reversed from last time, and that's why we saw nothing at all. That's not really possible, is it? Wow, this isn't very good. That's not normal, is it? Just spin that like that? That's what I got. Carry on. So the trick here was put lead to here. Okay, so break the current. Amps. And we'll check our resistor setting here. So we're on the times 1,000. So there's a huge resistor in here right now. Yeah, I remember now. That was the last thing I was doing. 7,000 was what it says in the book, although I don't really understand what's really being meant by that. 7,000. We can find that out this way. So that's 5,000 according to the 5,000 ohm resistor now in the plate circuit. So now I want to take my scope. I want to read between the cathode and between the resistor and the tube is where I want to read. So that would be, let's think about this now. This lead here. So this is the lead here. So I want to read on a lead that's not exposed anywhere. Yes, it is. It's exposed here on the tube. So if I pick off the plate, no. Yeah, I think this will work right here. Let's try it and see. Well, I don't see anything just yet. Of course, I don't have any voltage on the tube. Okay, are all meters happy? Everybody running? Still got a funny reading here. That's because this isn't switched on. On. Still have a funny reading here. You know what? I cranked it down last night when I was straightening up my shop on purpose for some less than purposeful purpose. Okay, so we're up around the 14 mark. Minus 14 bias, and now we'll bring up the B plus. And can you still see that meter? You can kind of not see it anymore. So I'll put this meter on the 150 volt scale. We'll take it up to 150, so you see a full scale indication on here. When I get to 150, here we go. It's 150 and there's no current flowing. So put this resistor in the circuit. And no resistor flowing. The wait a minute, what's going on here? We got current indicated on this meter. I've done something incorrect here. Current is coming out here. It's going through the resistor. It's coming from the resistor into the meter, out of the meter. So how does this thing read? How does this work? How does this work? It's not set right. It's not set right. Amps, milliamps, not set right. Not set right. Take down the B plus. Move this lead over here. So interestingly enough, it was passing current but not registering it on the meter. Oh, I know why. Let's go back there. Milliamp. Think. I think we're ready this time. I think. Any minute now, the meters are gonna start quitting. Here we go, going up. Watching for the 150. Okay, we've got a current flow now. That's good. So we don't want the current to be over 30. I've declared that the danger zone. So 15 milliamps. With a voltage of 150 volts on the plate. We still have a slightly low voltage here, slightly high current there, and this is really dead on. Proper C minus, although we have a low plate voltage, so this is probably a little high. I bet you if I back that down, I can quickly get this up. So back it down, and there it goes up. Pretty easy to do the static test at this point. Pretty hard to do the dynamic one. There's still nothing on the oscilloscope. Have I not got this sensitive enough? They're both on. Okay, now they're both on the same sensitivity. Look, this is not reading right at all. What have I done here? So the negative is. Here's my pile of negatives hooked back to the cathode. 8, 1, 2, 3, that's all correct. 8. Cathode grounded out on everything here. scope, both grounds going to the cathode. The other one scope lead going over to read the grid voltage. How can that read that? No, read the grid signal. Don't say voltage, say signal. It's on the other side of a capacitor. We're seeing the grid signal on the scope. So that scope connection appears to be working okay. That's probably the worst case, when things seem to be okay and they're really not. The other scope lead is here. So, I've connected it right onto the plate. So it's watching the plate voltage. Now the plate voltage should be dividing against this resistor. There's plate current flowing, so there's no doubt there's current going through the resistor. Just for a moment, it's just, anybody getting warm in here? Cold as can be. Where's the... It's actually over here. Oh, yeah, a little bit of warmth. Oh, yeah, definitely. Definitely warming up, but nothing bad, but definitely warming up. So we have all the evidence in the world that there's current flow. Now the screen voltage is being handled by matching it with the plate voltage. So the plate and screen have the same voltage in here. That's interesting. Now thank you for the comment. When I'm moving the plate voltage up and down, I'm actually moving the screen and plate voltages up and down. They're tied together. They're the same voltage. So this tube is not in its normal... I was going to say it's not in its normal operating condition, but that's not necessarily true. The tube manuals suggest the plate and screen are the same voltage. So getting back to the real question at hand, which is why can't I see an output from this tube now? Is it because this capacitor this is just a stupid arrangement? So I'll move the test lead from the scope right up onto the grid. This is the grid, so don't do that. Do it over here. This is right on. This is right on it. Well, let's change this resistor a little bit here. Not too much, but just a bit. Higher is definitely better. Let's go really high. Oh, now that's so high. Okay, see what's going on the scope there. It's like an open circuit. Wow. Okay, so we're 16,000 miles away from getting this to work. That's how it seems to me. If you look back in history, when early experimenters were doing stuff like this, I mean, obviously you're not doing it with a vacuum tube, doing it with other stuff. These guys invested their entire lives into finding out stuff like, if you wave a magnet near a wire, it'll make a galvanometer do this. They spend their entire lives discovering this kind of stuff. I should feel pretty good that I'm able to do this in my own shop, even if it doesn't work. Oh, but it will work. So a possibility here is the bias is way off. And that is what's causing the tube to not amplify. I can't imagine that's the case. But what we'll do is we'll fool around with the grid bias here a little bit and see, this really looks like it's not even connected. That's really what it looks like. Oh, wait a minute. So I have the supply come in through the resistor into the tube. All I want to do is get between the resistor and the tube. That's my head beeping this time. I'm getting an idea. That's my head. All that does is tell me I got this done right. Again, my meters are arguing with me here. Well, yeah, go away. You can go away too. Maybe that was the close but no cigar tone. Well, I can stand and stare at this for quite a while and not. I need new synapse connections for sure. Maybe my old ones are breaking. I'm going in the wrong direction. Okay, I'm going to stop for a minute and calm myself down and see if we can't surmount this question of why can't I get an output, or at least see the output. Maybe I'm getting it, but I can't see it. Okay, let's take a look at a diagram here. So here's my power supply up here. So this is the high voltage supply. This is the decade box resistor here. This is my ammeter. That's this meter sitting here, which has also gone to sleep. Positive comes through the resistor, the meter goes to the plate. Negative lead is tied to the cathode. Okay, we're putting something like 150 volts here to get things going. That causes a current flow. I'll show it this way. That's somewhere in the range of, say, 15 milliamps. I have that going. And then, oh, there's another grid in here. That's the screen grid I'm drawing. Getting this, yeah, screen grid. Just tied solid. I'm showing it inside the tube. It's actually outside the tube where it's tied solid. So here's the grid coming out. Grid potential is coming from here. I'm just going to draw it over here. Put C minus, put B plus here. C minus is coming down the, no, I didn't check this before starting up the, goes down here. So here we have a common and the supply, which is negative. Supply line is solidly connected there. This common is over to here. Cranking this up to around minus 14 volts. I got a signal generator. Let me draw it down here. Signal generator. The output, so there's a common and a signal output. Common output is right to here. That's on this black wire here. You can see it going to the common point, and the other side is connected to the grid through a capacitor. So I've connected it through a capacitor so it won't disturb the voltage being put on the grid by the supply, which is not this, it's back in here. That's why the capacitor is there. So if we want to show that, we would show it. I'm so critical of other people and their schematics. Look at this one coming here. Let's show it here. Let's do it like this. We'll show this extended. Cross without a dot. No connection. Down to here. This is very low impedance. On the other side of the capacitor though. So I have the signal going in, and we can see it on the scope. You can still see it. It's sitting right here. That's the signal going in, or signal on the grid. I shouldn't say going in. I don't know what's going in or going out yet. Sure appears to be impressed properly onto the grid. Now where exactly is the scope I just looked at? Where exactly is it connected? So it's connected, it's actually connected out here. Oh, you know what? That means if no signal is getting past this capacitor, if that's the case, we wouldn't know it because I'm monitoring in the wrong spot. Let's get on the other side of that capacitor. It's a scope lead, its impedance is very high. Let's do that. Okay, so it should disappear off the scope. And now, will it reappear? Maybe not. It does not reappear. So therein lies my problem. I'm trying to jam a signal into this tube and it's just being lost across this capacitor. I thought that was a pretty big capacitor. But you know, it's a capacitor hooked up to what is essentially almost nothing. It's hooked up to the impedances of this meter and my scope. So why would that matter? Why would that matter? What do I have to do then to see, to know the signal's getting there? Get rid of this capacitor. If I get rid of this capacitor, then I'm hooking the output of my signal generator right to a spot where there's a small DC voltage. I don't 12 volts. I don't think I want to pump 12 volts. So what's going on with this capacitor? Or do I need a resistor from the grid down to the cathode? Would that somehow help? That might do it, you know. Let's try that. Unfortunately, I used up my decade boxes here. So we'll have to try with just a resistor. Now, what would be a good resistor? Typically use very large resistors in this position because you don't want to reduce the impedance of the grid, but you want it large enough to bleed off any static charge. That's, I'm using the word static to mean standing. Any standing charge that's building up on it. Now, I've got some meters hooked up here, which, couldn't they play that role? Like, this is probably a 1,000,000 ohm input impedance. Doesn't say on it. That's this meter. They're all really high impedance, at least 1,000,000 ohms anyway. So I got a mega ohm. That's typically in the range of what you put in a resistor to bleed down the charge here. So in effect, don't I have it? Don't I have it twice? Because I also have the scope here, which with its 1,000,000. So we got two 1,000,000 loads on the grid. That's 500,000. That's right in the range of a resistor. What the heck is that? Is anybody looking at my scope? Watch the upper display as I scratch my bench with my hand. Hello. What's going on now? Oh my gosh. Okay, so this is getting to be a little more interesting now. Why would I see that on the output? The output is this upper one here. First, I have it set pretty sensitive here, 0.1 volts per division. It's fairly sensitive. What if I just grab onto that grid with my hand? Let's start with this part. And if I actually grab the grid itself, And that's the plate. That's the plate picture changing. Is it a loose wire causing this, or? I mean, it could be anything. It could be some kind of capacitive effect from all these wires sitting here, and I'm tapping on the bench. The wires are moving a little bit. And it's causing this effect. You know, basically anything. I'm a big effect here too. Anything I do is. Well, that's another thing about doing this whole kind of test. If you operate with very high impedances in here, then tiny charges push the voltage around. Charges that come from capacitive effects and things like that. But where is my grid output? Why is it like this? Okay, I've just totally lost my mind here, that's for sure. Totally lost it. Right, so we're on the grid looking at the grid itself. And is that really the grid? If I muck this right up, oh, I can't make mistakes like that, can I? Can I make mistakes that bad? The grid is 5. Yeah, that's no problem. For sure that's the grid. Well, defective capacitor. Nah. I just don't want to put 12 volts into the front end of my too many options, too many things, too many, just too many. Okay, let's try sticking a resistor on the grid. And I'll pick a nice sized big, we would want like a 10,000 ohm resistor, something like that. Something like 10,000. So it's significantly different from the here we are. It's got to be 10,000 here. Yeah. Significantly different from the impedance being presented by the scope and the grid voltage meter. So here's a 10K, and I'd like to run this between the cathode and here. Okay, I'm going to use clip leads. Yes, it's a real mess. What I'm hoping will happen here, but fat chance on it, is somehow by touching this to the grid, I'm going to see an output on here. Wait, there's no input. There's no input. Wait a minute. Wait. Yeah, actually, I should see it here, too. See them both. Here we go. What are the chances? Nil. Let's try it. Well, it does have an interesting effect. It takes this curve and kind of reverses it the other way. Look at that! There it is. We saw it. You saw it, I saw it, we all saw it. Did you see it? Maybe you didn't see it. You were watching my hand? Don't watch my hands. Watch that scope. There she is. Just exactly what we're after. So that's a 10,000 ohm resistor shorting out this capacitor. Maybe that's a tiny capacitor and it looks big, but it isn't. Let me get one that looks big. One there's no doubt about its big, powerful. Big and powerful. So I think this is a 0.1. Sometimes what I think doesn't really... Hey, another meter. Sometimes what I think doesn't really matter. Let's see. 0.1. That's a big capacitor. Okay, let's change this out here. easiest way to do this would be to clip this like this. I just took the, hopefully I didn't interrupt the bias. I don't want to interrupt the bias of the tube operating. And then we'll take this and we'll just feed it through the bigger capacitor. Watching the scope now. Come on out of here. Son of a gun. I still got that shakiness. Well, anyway, now we've gotten certainly a big step forward. Now, let's compare these. They're both set to the same. They're set the same. So we see input and output. So the output voltage is, hey, we got somewhere. We got somewhere. And what is the amplification factor right now? Now, just looking at the scope, 3. Okay, let's just review everything now. Okay, come on, all meters back to coffee breaks over, guys. Back to work. Okay, starting with the grid, the heater. Heater's at exactly 0.7 amps. Perfect. The voltage causing that is 6.1. Grid bias is minus 12, but the plate is very low. This is a 150 volt scale, so we're looking at 75 volts on the plate. So we're nowhere on the plate. So I'm now going to change this to show a factor of 10. So this scale differences here is a factor of 10. So to get this, if you want to compare this to that, you got to multiply this by 10 to compare it to that. Okay. So I'm getting ready to raise the voltage. I'm expecting this to get bigger and bigger. This shouldn't change. The input shouldn't change. The output should get bigger and bigger. And we see our current flow through the tube is negligible at this point. It's barely operating. Cool, but it's actually amplifying. I think that's what's going on. Okay, raise the B+. We'll raise it first to 150 volts, which is full scale here. And we'll watch the scope and the meter, watch everything, watching everything now. Oh, what's going on? It's not going up. Okay, so this was a problem I ran into last time. So we're actually putting out on my supply 250 volts. We're hardly getting any, making it. So what's happening is most of the voltage is dropping across this resistor. This doesn't quite make sense to me because the internal plate resistance of this thing is 80,000 ohms. So if it's voltage dividing, then until you get 80,000 ohms sitting over here, or if you had 80,000 ohms sitting over here, you'd expect half the plate voltage. Like they would just divide it in half. That's not what's happening though. So we think the supply is around 250. The heart getting to the tube is around 60. So 200 volts dropping on this resistor, which is probably getting pretty warm. So this is set to, so this resistor could be something totally different from what this panel shows. This shows 1,000 times 1,000. Oh my gosh, this is set to 1,000,000. I think that explains everything. I think that explains everything. So we don't want this at 1,000,000, we want this at around 7,000. So I flip this up and flip this over. Watch the big change. Big change here. Okay, so now we can get to the 150. We got 15 milliamps. What's happening in here? Smoke coming out of this yet? We're hooked up over here. This is a tough way to find out. Find out by screaming. No heat building. Good. I think that's good. What do we got happening now? Minus 12 on a 150, so this is still probably too high. Let's reduce this because it's 14. It recommends minus 14 at 250 volts. I'm only at 150. Let's crank it up higher into the range where it's the operating range, normal operating range, or the. We'll see what happens here with everything. Here we go. And I got a limit on my supply here too. So we're on our way. So the amplification, looked like it got a little better. I'm at the top. That's it. There's no more juice coming out of my machine here. So I'm going to set it just below the top of its power. 350 volts coming out of it. And what's making it? 500. We're still at just 150. So this resistor is costing a lot of voltage here still. And now what kind of, let me flip this back so we can see these one for one. So that's the kind of amplification we're getting. We're in one division, we're coming out 1, 2, 4 divisions. So 4. I think you can call that the mu of the tube. The mu of the tube or the circuit it's in? It's the circuit it's in. Okay, have I reached the point where I've done so much my head is chock full for the day? Interesting question would be, why is this clip lead laying out here? What was I going to do with this? I think this was part of my plan up in here. Let's get it off. Okay, so if we wanted to actually try and, oh, this is low now. This should be higher, I think. If we want to try and determine the GM at this point, the dynamic GM. Wow. If we assume this has the voltage across this resistor, and if we assume this resistor is actually 3,000 ohms. Oh my God. Yeah, right. I don't think I'm going to even finish those thoughts off. The main thing is we have this operating. It's definitely amplifying voltage-wise. The external elements around here are probably interfering with this whole deal. You can calculate GM by knowing the mu and something else. So I think, and no, don't quote me on any of these things. Okay. I think the mu is the amplification factor, and I think it's 4 right now. Let's leave it at that. Let's leave it at that, because it's a beautiful, sunshiny day, and but cold. But still, love the sunshine. None in here. So I'll see you on the next video when I try to do, I don't know what I'm going to try to do. I got to do something now. I got to get serious about trying to measure the GM. I think I've reached the point where we can seriously attempt something here. Seriously. See ya.